Alright, welcome back everyone. Welcome back to the video lectures. This week we will continue talking about text data, and specifically this will be continuing on more issues with text. So in particular some specific examples of where language can form some complexity when interpreting this particular type of data. And then we'll be looking at a practical example of document classification. We'll be introducing two new algorithms, so this will be naive Bayes and support vector machines, and then we'll have an example on real data, real application, and hopefully give you a bit of intuition regarding these two classifiers that we're introducing here. And the first point that I want to get into is how to pre-process noisy text. And this image sort of elucidates to the fact that when we look at language specifically, there's just regular patterns, but generally there's some overall semantics, so some higher level meaning to it that is very hard to interpret if you don't have certain world knowledge or a higher overview of the meaning behind the simple flat text that you're seeing. And this can easily be overlooked when applying, for example, very naive ways to clean text data. Now, often people dealing with text that aren't necessarily interested in language just see it as sort of a vessel that holds a bunch of tokens, and maybe we can subtract some higher level information from it, but they don't necessarily deal with the sort of complex nature of language as a container for information. So one thing that you might commonly see is that when dealing with text data, there's these sort of complex tokens and we don't really know how to deal with them, so we just get rid of everything so that we have this very clean, no frills representation, and we'll hope that in the end the model will just sort this out for us. So here's a very simple regular expression. It removes all the characters that are not alphanumeric or not a white space, and then we're left with this sort of clean form of text. But obviously we wouldn't be talking about this if this would solve everything. So the first thing that we'll be looking at is how do we actually find complex tokens rather than just splitting on white space. Now, one of the more well-developed and high-quality packages to deal with natural language data is spaCy. It's an alternative to NLTK that you might have heard of. spaCy is more recent. It has some very fast, high-quality models, and therefore for many tasks it should be the package of choice, including the task that we're going to talk about today. So it's quite straightforward. We just import the packages and we load the English models, and then we ask it to do a linguistic analysis of the text that we're providing it. And already we can sort of compare that when we have the original. How does just splitting on white space compare to doing actual tokenization with some knowledge about the linguistic factors that are in this data? So for white space, we can see that we have what we would expect. So there's I can't watch Marvel's Dr. Horrible. But we can also identify certain errors that we might not think are actual separate tokens. So one of the examples is that can't is actually a merger between can and not. And we might want to consider these two as separate tokens, because then we might know that there's not in there, and that is actually a negative way of phrasing this. Whereas otherwise we would have to have a separate representation for all the word forms that not can have, so can't, don't, won't, and these will all be different tokens to our model. Now, one of the other ones is the possessive, so Marvel's, which is Marvel its, so we would want to split that as well. And then obviously at the end horrible, and then period. Period is not actually part of the word horrible, so we would want to split that off. But for this we need a sort of sense of where the sentence ends. Because here, as you can see, we have Dr. Horrible and there's already a period after Doctor. So if you would use period as our sentence ending, this would already have broken off after Doctor. And obviously, if we do a more deep linguistic analysis, we might identify Doctor as being a common abbreviation for the full word Doctor. and therefore the period after dr not being an actual sentence stop. So this is where using a actual natural language processing tool can help you to better distinguish the information that you're provided within this one sentence. And hopefully here you can sort of see where we're moving towards. We want to have a sort of uniform information signal from the text that we're provided. So we don't want to confuse the model too much with the fact that we have sort of complex constructs in language, and we want certain words to always look the same so that they can always be interpreted the same by our model and won't suffer from certain spelling variations or, for example, grammar variations. So one of the things that we might consider is the fact that if we have certain tenses, that words vary. So I was, I am, I were, all these kind of things, basically it's the same verb, right? So it's the same token of information, is just in a different tense. And why this could be informative, sometimes we don't actually want to consider the tense that the sentence is in, so we can sort of try to neutralize this. And this process is called lemmatization, so it doesn't consider the ways that we're altering the words by making them past tense or by changing anything else about their form. So the verb is watch, and if we're watching or watch, and whether we give watching or watch to our model might not be too important, but if we give too many variations of the same word, it might at some point not notice that this is actually the same verb. And especially if we're looking at sentence contexts, so more than just the single words, we already have very little data for many of the words, so we also want them to be as uniform as we possibly can make them. Now, apart from that, there's a sort of more computational perspective to this, which is that incorrectly identifying tokens and lemmas will very much blow up your vocabulary and therefore, at least when dealing with text data, your feature space. So for example, if we look at this sentence, if we had I am here, then any time that we would have I as an occurrence here, we would actually have the word I and am, and these are probably very frequent words. So if we don't separate these two tokens, any sort of different form of these is going to have a different entry in our feature space. And the same holds for words that, for example, have a period, like ball. As you can see here, we have ball with a period here. We also have balls. And to our model, it might actually not be important if we are talking about ball at the end of a sentence. If we're talking about the plural form, we would all want these counts in ball right here. So we know that for all these three sentences, actually the word ball is in there and it's talking about a ball. So as you can see here, with a very naive white space splitting of the tokens, we have a vocabulary length of 18, which, given the fact that we only have 3 documents, is actually a lot, especially for these very short sentences that we're considering here. And note that the feature matrix here is actually longer, so there's more in the vocabulary. I just cut it off because otherwise it would actually go past the screen. So what actually happens if we normalize these words as much as possible using proper tokenization, so linguistically informed tokenization, and then lemmatization to try to make these words as uniform as possible. So for these 3 documents and these very short sentences, it doesn't make that much of a difference, right? It's just only 4 in size that we've reduced the vocabulary. However, if you think about the sort of ways in which we've presented the information here, so bowl is probably going to occur a lot if we have a lot of documents, and it's probably going to occur very little with a period after it. So the bigger your documents, the longer your documents, the more documents you have, the more your vocabulary is going to blow up if you keep this mess around in your data and don't properly separate everything. And this becomes even more complex when we try to deal with tokens that might exist of more words than just one. So let's say, for example, we're dealing with movie review data. It might actually be very interesting to us to have these sort of pairs of words. So for example, if we're talking about a single actor, we might want to consider this as a single token. This is pretty specific to the use case that we're considering here, but it might actually turn out to be very important. So just considering someone's name could be sort of ambiguous. So for example, Alan could be a very common name. Turing might not be such a common name, but anytime that we are referring to Alan, we would want to know that it's actually referring to Alan Turing in full. But even more importantly, certain titles of movies, for example, might give our model the idea that we're talking about a game. So this small piece of text is dealing with some kind of game. Well, actually, it's dealing with the entire movie, right? So the imitation game right here. And when we're interested in these specific entities or sort of complex constructions that might be made up of multiple words that we might want to consider as one token, we can turn to named entity recognition. Now, named entity recognition is a natural language processing task, often involving machine learning, where the task is to find patterns that might indicate that some token is actually, for example, a person or an organization. It could also be a location. As you can see here, we can actually use spaCy to extract these from the text for us, and when we print this label for each of the entities that are within our parse document right here, we are provided with this nice list of what spaCy thinks are the entities, and it will also give us this class. And as I said, depending on our use case, we might actually want to consider these as one vocabulary entry rather than more than one. Now you can imagine that with social media text, this kind of pre-processing becomes even more important. And this is quite obviously due to the fact that there is a lot of spelling variation in social media text. A lot of the words can be garbled, they can be written in a specific style. We can have to deal with slang, certain variants of spelling that are maybe within a certain dialect or a certain region or a certain age group. We have smarties, emojis to deal with, and all these kind of things introduce a very hefty set of pre-processing material. So it's therefore no surprise that this is a sort of research field by itself, which is often referred to as normalization. But then for language, so language normalization. So this would turn what spaCy thinks the token should be here into plain English, like shown in the box below. Now note that there's several specific points that it makes improvements on. So other than knowing that Lord maps to Lord, and girl maps to girl, there's also a reduction of flooding characters, as this is called, like in stupid. Also in the very long lol here, it maps correctly to this one right here. And then for the latter part, spaCy does recognize sort of simple emoticons like this one. This would be correctly tokenized, but longer ones are generally not recognized, and it ends up being this part over here. So it's important to train these kind of tools, or at least use tools that were trained on the platform that you expect to use them on. So this can be very different for formal text compared to social media text. Now, having covered these sort of basic concepts where natural language processing might be able to help you out with interpreting text data, we go into the meat of this video, which is document classification. Now, document classification is very similar to regular classification, just that all the instances are text only and are space, therefore consists of words, and the documents are vectors. So any of these might be, for example, the document, and for example A. So these are the axes, right? And then a single vector within this space is then a document. And similar to what we've seen before, we can, for example, with K and N, determine the similarity between two documents. Now we might also extend this into, for example, an information retrieval problem where we introduce a certain query vector and then we measure the similarity between our query vector and the documents. So this was just recapping on what we've talked about in the previous lecture, and this is what we call document classification in general. So there's a target that relates to whatever we want to predict in these documents that we have as input, and there's a specific set of features or a vocabulary that we hope will help us in solving this task. Now, one of the very widely applicable tasks that deals exactly with this is sentiment analysis. Now, sentiment analysis is pretty straightforward. We have a piece of text, and the only thing we really want to do is say if this piece of text is positive or negative. Or we might introduce several other categories like neutral, highly positive, or highly negative. And given the input vectors, we want to make a prediction between any of these labels right here. Now, simplified, this usually boils down to we either have positive or negative or neutral, and then some of the advanced data sets also include these 5-point polarity scales. Now, if we stick to our sort of movie review case that we were discussing, this might look like this box over here. So this is a review, a negative review for a well-known cartoon that, as you can see, has a bunch of words in there where we can already sort of intuitively say that this is a negative review. We don't need to see the label for this. There is crappy episodes in here, mediocre, bad improv jokes. So it's probably unsurprising that this review was given a 1 as a score. But as you can imagine, we don't always have this very clear opinion within text. We do want to uncover a certain sentiment score for example, tweets, or generally any other piece of text that we might think has some sentiment to it. So this sort of excludes formal writing. Now, the way we would normally go about doing this task is that we collect some data, and as I said, preferably where there's very strong sentiment, because when we're training to solve this task, we actually want there to be strong indications of either positive, negative, or neutral sentiment, so that when we hire annotators, so these will be people that go and look into our data and then do manual labeling of these instances so that we actually have a prediction target, have a strong signal of the opinion or sentiment within that text. So say you employ a bunch of people and they get a lot of neutral text or text where it's not super clear what the opinion or the sentiment within this text is. They're going to have a lot of disagreements if it's neutral or positive, and this is something that, at least for annotation, you generally want to have very strict guidelines on, and therefore also provide them with data that they can actually annotate without too much trouble. Now, once they've provided us with these labels for sentiment, we can represent the text that we provided as vectors, give this annotations as a target. So this would just be looking at the documents providing negative, positive, or neutral, and these labels we then just treat as a target. And hopefully, if we train a classifier correctly, we are left with patterns within these sort of word frequencies that we've represented that help us to determine sentiment for a specific text document. So this is just employing a classifier to say this document over here is positively written, or has some negative sentiment to it, or is just neutral. And preferably we would also want to have a certain strength allocated to this, so if something is just mildly negative, that's also interesting to know. Now I think another more interesting way to do this that will also not cost you a lot of money is, rather than doing complete supervised learning of this task, so where we provide accurate labels, we do distant supervision, and this is also sometimes referred to as weak supervision, because we have some assumptions on if our target is correct. This is quite an important concept if you're working with limited resources, or just want to generally get some classifier together without doing a lot of work on labeling or employing these annotators for you. This can be of huge help. So let's get into how this works. The first step is basically exactly the same. So we get our data, and this doesn't change. So preferably we would want that to have a strong sentiment, and then rather than doing this annotation, we try to gather data that already has sort of an indirect signal that might indicate sentiment. And I kind of alluded to this earlier, but review score is actually a very good platform where there is strong sentiment, and we also have a score sort of attached to these reviews as sort of a byproduct of the data. It's not necessarily referring to the sentiment. There might be very positive sentences in there as well, but we assume that overall these review scores will be correlated with the sentiment. If there's a very low review score for a bad movie, overall we assume that this has a negative sentiment, so that the majority of the document which we label to be negative is actually negative. And subsequently we assume that high scores will also have positive text. Now notice that this is weak or distant supervision because we might actually be labeling certain sentences that have some actual negative sentiment as positive, but we hope that in the end the majority of the sentences will actually be correct, and therefore we will overrule some of the noise that we're introducing in our labeling like this. And as I said, because we don't require this annotation, basically it's free, right? So we gather data, we use some metadata like review scores to be stand-in for the manual labels that we would otherwise get. And because we don't need annotators and they don't need to go through all our data, we can actually get more data. We only need to focus on collecting, and we don't need to focus on developing annotation guidelines, testing if these annotators worked well, investing some money in Mechanical Turk. We can just get whatever data we want, and we can also have a certain evaluation that might have some hand-labeled instances, so that we can, at least we have a reliable test set. But for the majority of the training data and maybe also the validation data, we can just rely on this distant supervision. So I think sentiment analysis by itself is already a pretty interesting task, so I've included an actual example in these sheets. So we might also want to talk about some of the challenges that this poses, because obviously it's not that easy as just looking at some word distributions and then already making a very accurate prediction, because as I said in the previous practical, language is complicated. Humans aren't really effective in being unambiguous in communicating their information, or spreading the information in some way that it's, you know, it's very easy to interpret what's meant in a sentence. So I've prepared some problems here. Now this list again is not exhaustive. It's just what I came up with top of my head. So one of the easier ones, I would say, is negation. So take into account that a model only sees this as a bag of words representation that we also talked about in the previous lecture. So these words are just scrambled. It doesn't know about the order of these, at least not yet. So one of the things that we might do to solve negation is provide a bit of context. And this we can do by, rather than just focusing on single tokens, we focus on pairs, maybe even triplets. And this is called n-gram features, where n is the size of the window that we consider to make a sort of chunk that we see as one feature. So say that we have 2 grams, for example. This movie is going to be one feature, movie is going to be one feature, is definitely is going to be a feature, etc. And then in the end we will end up with not bad. So because the classifier knows, or at least has some information that not was actually just before bad, it might actually give this a positive sentiment. So we can already fix this with a pretty easy method where we just include a bit more of the context. Now, as you can probably figure out yourself, we can't include very, very long grams, because the more words we include in this window, the rarer this feature is going to be. Somewhere from sort of north of 4 grams, this exact combination of words is going to be very rare. This is just how we humans use language. It's creative, and therefore certain constructions of sentences are actually very unique, and this is why we can't look at very long dependencies here. We can only focus on these sort of small chunks. Now we can concatenate 1 grams with 2 grams, so then we have these single tokens but also doubles and triples, and this is how we get sort of a complex representation. But do note that this also very much blows up your feature space, so you'll have to do some reduction or decomposition afterwards to account for this. And this is also not necessarily restricted to tokens. We can also look at character, so character n-grams or character grams, and this would, for example, for 3 grams, we would consider the, and then his, and is, white space, etc. You can sort of work this out for yourself. Now, one of the things that this does is that it sometimes when things are misspelled, at least the surrounding grams are still going to be okay and sort of have this representation of the word that's still close to the old one. Just one of the grams is going to look somewhat funny, but it turns out that classifiers are actually able to recognize that that would be the other word, and therefore they become somewhat invariant to spelling mistakes. Now, obviously not totally invariant, it's just a sort of quick way to deal with this. However, consider the fact that in language there's usually very long dependencies. So if I start my sentence here, it might be the case, especially in languages unlike English, that don't have this sort of build up that is custom to constructing a sentence where you have certain ordering of time and objects and these kind of things. It might be that whatever we wanted to negate bad with is way at the beginning of the sentence. So this is somewhat the case, I think, with this sentence right here. So whoever thinks this film is incredibly bad is an idiot. We have to somehow know that incredibly bad relates to the movie or the film right here. But we also have to know that whoever, and then this chunk right here, is an idiot. So this is actually negating the fact that we might consider incredibly bad negative sentiment, because we mean that is actually good, right? So this is a very long dependency that we somehow have to resolve by looking at a very complex representation of language. We can't just do a lookup or something because it's not super clear how the sentence is constructed. At least we can't cheat and use some grams and fix this way. Now, one of the harder tasks definitely is sarcasm. So this is a very blatant example, I think, of sarcasm. So just looking at single tokens or grams, we might say that, okay, it says best movie ever here, right? So this must be a super positive review. But actually this one over here, this might betray the fact that it's actually meant as being sarcastic. I mean, it's not a guarantee, but it might give us some strong signal that maybe this person is not being very honest. But to the model, this is probably lol is used in a lot of positive contexts as well, so that makes it extra confusing. You have to really dig into the fact that a certain statement regarding a certain sentiment can be negated with sarcasm for this to actually work out for your task. And I think the hardest one by far is having context, like actual context or world knowledge. I think it's better described as. Now this is where to solve a task we need to know way more beyond the scope of the task. So for this one specifically, saying that a movie is only slightly better than some other movie, it can be very negative, but it can also be very positive. So Jaws is widely regarded as a very good movie, and knowing that, saying that this movie is only slightly better than Jaws, it might be a funny way of phrasing it, but if we know that Jaws is actually a very good film, then we might say that this actually has very positive sentiment rather than this sort of slightly negative that we are assuming now. But for this, again, we need to know what the score of the film of Jaws is to actually fix this. Also, we need to know that is actually in the sentence, right? So we need to know that there is being conducted some comparison here between a movie over here and Jaws, which is also a movie over here. So I think this is a very, very good example of natural language processing that is definitely not solved yet. There's no deep neural network or any other fancy methods that can deal with the complexity of these kind of problems yet. So let's look at some of the solutions that people have come up with for at least some of these tasks. So this will be sort of NLP research. All of these challenges are basically research tasks on their own. So one of them is solving these dependencies. One of the things you can do is run a sentence through a dependency parser or some other model that knows what kind of word types there are in, how they relate to each other. So you'll get the output that is similar to this if you do that. Now, you don't have to know what these are all about. This is sort of stuff if you're interested in natural language processing or text mining. These are very good things to know, but it's definitely for this course, it's not necessary. It's just I think it's a very good example though. So I've parsed this sentence, whoever thinks this film is incredibly bad is an idiot, and you can see that here there's a dependency between things and whoever, and it also has this long dependency from whoever thinks, which goes to is and then an idiot. So we can sort of solve the compositionality of this sentence by following the arrows that are shown here. Now, sarcasm detection, I think, is very hard. In general, it's still definitely not solved. I have provided one example here, which is the Deepmoji from the MIT Media Lab. Basically, what they did is look at the co-occurrences between certain emojis and certain word use. So hopefully by that they solve these kind of things that are actually negatively connotated, but due to the fact that there's a certain information that might be misleading within these sentences, this is obfuscated somehow. So let's try our example sentence. Best movie ever. And what you can see here is that it's actually associating this with a lot of positive sentiment, even though it might have been sarcastic. So let's try to make this even worse by saying not. And as you can see, it already changes the emojis associated this to one that you might associate with sarcasm. It increases somewhat the confidence of it being sarcastic, but it definitely doesn't solve our problem. Now, one of the things that it probably has a bit more information on is the examples that are included in here. So if we click the one, my flight is delayed, amazing, you can see that this is associated with a lot of pissed off emojis. Maybe because of the periods, we can actually try to change this. Maybe change it to an exclamation mark, see what that does. Now, as you can see, it's still steaming emojis. There's one thumbs up, but for the most part, having your flight delayed is probably never associated with a positive sentiment. So the only positive word here would be amazing, and then delayed is very heavily influencing the decision of this particular sentence. So I think we can even click this one off, and you can see that this changes the sentence into my flight is amazing, and then immediately we get the positive emojis back. So again, using this these emojis as a signal is a form of distance supervision for sentiment, and also for this sarcasm detection task, and makes this actually a very neat application. Now, the more complex one I was referring to is world knowledge. Now, obviously, using Google to answer what the average rating for Jaws was is not going to solve this task. Then we would need something that could actually come up with the question that the movie was compared to Jaws, and therefore we need to have the score that was associated to Jaws. Obviously, this is very complicated, but this is at least to some extent showing you that with information retrieval, or sort of question answering, we can try to solve these sort of complex tasks. Now, you might say I can pose any problem I have in a question, like what is the sentiment of this particular sentence, and you need to provide the sentence. So this is definitely something that in question answering is not solved yet. But these kind of information, factoid sort of pieces of information that we can collect, this is actually being worked on by Apple, by Google, by any of the sort of personal assistant driving companies, and it's a very lively research field. And I think Twitter in general is actually a very good platform for these kind of applications of sentiment analysis. It does give you some very constrained input to work with, because there is a character limit that was, at least at the time of recording this video, tested to be more than just 140 characters. It's up to 280. And as you can imagine, a lot of researchers are now banging their heads, because the classifiers they trained on these very short inputs might actually totally change, not only due to the fact that length is different, but also due to the fact that the vocabulary that people use and certain constructions or contexts that were previously within a very limited set of parameters now have actually doubled, and that opens opportunities for way more complex sentences and more elaborate communication of information. And one of those tasks that will suffer from this is definitely sentiment analysis. Now, nevertheless, Twitter, being a sort of open stream of information, provides many sort of interesting fields that we can look at, applying sentiment analysis, and see how sentiment within a very large population influences certain components. So we could, for example, use this for stock market predictions. If we see that the sentiment regarding tweets of a certain company, which we might be able to identify with named entity recognition, if that sentiment goes down, so starts turning more negative or more positive, we might see some fluctuations on the stock market based on this this sentiment shift, which very likely is related to certain news or a certain event that took place that made it so that this sentiment shift happened. So it immediately opens up an additional sort of research task that we can put on that. Same holds for predicting elections. So if you sort of monitor the sentiment that is placed on either of candidates, if we're talking about the USA, or multiple if we're talking about other countries, you might actually be able to say something about these elections. Now, similarly, this could be applied to brand monitoring. So say that you've launched some ad campaign for a company, you can see what the impact of this is, so what the reach of it is, what the certain response to it is, if it negatively or positively changes the opinions of your followers or your target group. This can be very important for people that are designing these kind of advertisements or have to do some interpretation of these kind of campaigns. It could also be used for web care similarly, so to sort of sort complaints from less severe to very severe and urgent. And it could also help to facilitate journalism, where if, for example, you are covering a sports game and it turned out everyone was very bummed about some particular team losing, and you know that these people are supporters of that team, you can write something about the impact on that team. You might be able to say something about the quality of the game. So if a lot of people are saying that it's boring and it therefore has a negative sentiment amongst both of the supporter groups, this might be interesting to look at. All these kind of text mining tasks can be off-shipped by just doing sentiment, basically, and looking at frequencies on Twitter. Now, this is all well and good, but I wouldn't be surprised if you would actually want to see this in action. So I've downloaded the Stanford Big Movie Review database, merged the positive and negative examples, loaded their labels, and we can then go into the part of doing text mining. Now, one of the important components is the feature extraction library from scikit-learn. There's a text one in there which has, amongst others, account vectorize. It also has TF-IDF that we talked about in a previous lecture. I'm just going to use raw counts for this for now. So this works the same as any other class that you apply to your data. So this is instantiating it. This is fitting and transforming your data. So now this these texts that were loaded here, so this is just plain text, is now converted to counts. So X now is, rather than being a list of strings with the reviews, it is now a matrix with counts for each of these words, etc. So then we split these into our train and test sets, and I wanted to show you what the dimensions are of the first instance. And as you can see, it's a sparse matrix. This implies that rather than encoding all these zeros that we generally have, and if you think about it for a bit, if we have a lot of documents, we have a very big vocabulary. But the bigger our vocabulary, the lower the probability that a word will be present in a document. Except for the very frequent words. As you might know, most human-generated behavior actually follows a power law distribution or Zipfian distribution, that if we put on a log-log scale, will be a straight line with a sort of heavy tail right here. This implies that words that are very frequent, so this would be, for example, the, are very, very, very frequent. And then the long tail, as we call it in words, have probably very, very long words in here that almost never occur. These are what we generally refer to as hapaxes. So very, very infrequent words. And if we don't put this on a log scale, it generally looks like this. So anyway, given the fact that language word frequencies within a corpus follow this, we can assume that from this point on we will have very many words that are actually infrequent, and therefore if we have a vector representation of a single document, it's going to contain a lot of zeros. Now, a way to efficiently store this within memory is to not have a representation for the zeros. So we're only interested in the ones that actually are non-zero, and then a sparse matrix format just saves the coordinates that they should have, at least the things that are actually one within this this matrix. So it will generally look like some coordinate and then some value. You can look this up if you're interested in this, but it's a very compact representation of data, and also it requires a specific set of classifiers that actually work on a sparse matrix format. So you might encounter some classifiers where you actually need to convert X to dense. The function is literally to dense, which will then convert it to this matrix format that we're used to, rather than the sparse matrix format. So now that we've set up our train and test data sets, we are going to employ naive Bayes, which is a probabilistic classifier on our data set. And for this particular part, we're applying multinomial naive Bayes. Actually, the one that we will be talking about further on is actually Gaussian naive Bayes. They just assume different distributions over the frequencies, but it's not necessarily important to talk about right now. Just wanted to show you how this looks like. So we have this naive Bayes classifier here, we fit our training data, and we do predictions on our test set. We just import this classification report function from sklearn that includes precision recall of one score, and also gives us the counts, so the supports for the different classes. Now here 0 is negative and 1 is positive. So you can see that we're actually pretty decent with this multinomial naive Bayes at classifying the sentiment, at least within the case that we don't have neutral documents. It's very important to consider that we're only looking at, is it positive or is it negative. Now you can imagine that if we would include a lot of neutral messages in here, this would complicate the classification task. So let's get into the standard implementation of naive Bayes. I think it's a very interesting classifier because different from some of the classifiers we've looked at, it doesn't look at this vector space that you are all familiar with now. It also doesn't look at splitting the data set in certain decisions as decision trees do. It only uses probabilities of features and their occurrence under a certain label. Now what this means is that if I have an instant X that is great movie, and this is for example a positive or plus or thumbs up, however you would want to visualize this. So if I have these words and this positive label, I'm interested in how many times do these words actually occur with a positive label, because if a certain word occurs a lot of times with a positive label, so it has a higher probability being a positive class, then that word is probably very informative when making a decision, right? If I see this word again during test time and it has a very high probability of occurring with a positive label, then it's actually a very informative feature. So this intuition is literally what naive Bayes depends on. Now there is some motivation from Bayes' theorem. Within this classifier, it makes some naive assumptions, but for this course it's not important to really know why this is different from doing some actual probability conditional probability modeling. We're just interested in how the naive implementation looks like. So this would be the formula given a vector. So this is the full vector in general, and the features, we're interested in the probability of these features occurring under a certain label. So what is the probability of a class being positive given, so this straight line right here indicates given. So what is the chance, P, probability of something being positive given the features? Now this is the very important assumption that you do have to realize how it plays a role in this overall model. We assume that all the features contribute independently to the classification, regardless of correlations between the features. So if we just measure the probability of a certain feature under a certain label, we do not take into account the interactions of these different features. We just measure their isolated probabilities and then multiplying these with the class prior right here. So the probability of the class actually occurring would give us the correct prediction for a certain instance. Now we're going to look at a sort of worked out example in the next slide, but I do want you to consider this the formula for doing the actual prediction. So y hat, so that's our prediction right here, is basically this. So we take the max, so the maximum value for all our y's. So say that we have y is so only 0 and 1, right? So we have two classes, and for these two classes y, we want to have the probability of those classes. So we will have a p for 0 and a p for 1. So this actually encodes two operations, and then this product right here, so this guy over here, tells us that we take the product over all the combinations of features. So rather than sigma, where we sum over this part, we now multiply all of the elements in this part rather than summing them up. So we iterate j, so we are indexing our vector, so vector, let's say x, by j, so that the first word is 1, so j is 1, j is 2 is the second element, etc. And then we get the probability of that word given this one label. Then we do it for the other label, but we do it for all of the features that we have, all of the instances that we have. We get the probabilities, we multiply them together, multiply them by the chance of the, or the probability of the label, and then we get a lot of probability scores, and we just take the maximum probability from all of these calculations. That's what argmax says right here. So we just, this says nothing more than we take the most probable of all the calculations that we did here. So it's just good to realize that this is how the formula looks like, and now we're going to try to actually calculate it, because that will give you a lot of insight into how this model works over just doing the math. So let's consider this feature matrix that we have. These are just regular counts. We are sort of approaching this from a binary representation because that's always easy. For this you would actually want to use the Bernoulli implementation of naive Bayes, but you sort of don't have to know that, at least for now. If you're doing scikit-learn, it's actually important to consider which values you're using, but for this example you don't need to know that this is the specific implementation that deals with this. But say that we have binary counts for these words. So these are the words, so this is our vocabulary. We have bad, great, and movie. Then we have our labels here, so thumbs up for positive and thumbs down for negative. So this is our target. And somehow we have to assess the probabilities of these words given the labels that we have. So remember that this was the formula. If you skip back, you can see that I've extended it with one extra feature because now we have 3 words, right? So we need x1, x2, x3. So it's the probability of a certain label given x1, x2, and x3. So at training time, this is very important to realize that this is exactly how the model fits the data. So it tries to determine the probabilities, and then this is at test time, where it actually does the classification on new data. Anyway, during training time, we are interested in looking up from this matrix that we have the probabilities of the words that we have given some label. So that's basically solving this part, or at least making sure that we have these probabilities available at test time. So at training time, we try to infer all the probabilities. So let's look at the probability of bad given a positive label. So we look at our bad column, and basically we try to see how many times bad occurs with a positive label, which is 0 times out of all 3 times that it could occur with a positive label, right? So 0 out of 3. Now we look at the next one. So great, how many times does that occur with a positive label? That's 2 out of 3 times that it could have occurred with a positive label. So that's 2 out of 3. Same for movie. Movie always occurs with a positive label, as you can see here. So that would be 3 over 3. So it actually has a chance of 100% to occur under a positive label. And then for the end, we do the same, but we just look at how much is actually the probability of a positive label. This is actually incorrect. This should have been 5. So 3 out of 5. This will mean that these are also not correct, but you can calculate it for yourself. It should be 5. And then this should be 2 out of 5. And this should have been 2 out of 5 as well. Anyway, so looking up, we have 3 out of 5 of the total amount of labels that we have. So the probability of a positive label is 3 out of 5. And then for a negative label, as you can see here, it's 2 out of 5. We do the same thing. So these are actually correct. We do the same thing with the other word. So bad has a 100% probability of occurring under a negative label, etc. So during training time, we just construct this sort of probability list where we can look up both a word and a label and then see the probability for that. Now at test time, we are provided with a new document, which is just bad movie. This is what it says. So it has 2 tokens. It has bad and it has movie. And now we're interested in seeing what the probabilities are. We just apply this formula over here to do a prediction. So the probability of a certain label given the features, this is exactly what we're doing here. And also notice that we're doing this for both negative and positive. So if we would add more labels, we would have more probability counts here, right? And then we just fill in this formula. We don't have feature 2 here, right? Because we only have bad and movie. So this one we don't need to consider. So we only need to get the probability of the first feature and the third feature, and then for the positive one. So we look that up. So x1 is bad, right? So we look up this probability is 0 out of 3. We multiply it with the probability of movie given the positive, so 3 out of 3, that one goes there, and then we have 3 out of 5, and because we have a 0 over here, the whole thing is actually 0. Now this is something that in general we try to avoid. We try to avoid zero counts because they will make the whole probability zero, and that's something with even if we have very low probabilities, we don't want them to be zero. So usually we apply something called smoothing, where we actually introduce a single count or something for the zero counts. This is the same as we talked about previous lecture with the TF-IDF, where we do some smoothing. We might want to do the same for knife Bayes so that we don't actually have zero counts that will make this whole equation. Never mind any of these, so these are actually very high probabilities, but if there's like a single zero in there, the whole thing will be zero, so that's something we would want to avoid. Therefore we apply smoothing. Now we do this calculation, this will probably be a bit lower, but nevertheless, if we don't apply smoothing and we calculate the probabilities here, we have two probabilities. So note that again, if we had more classes, we would have had more probabilities. And then we do this argmax operation that looked a bit weird, but now that you can see that we calculated the probabilities, it might actually make sense. We just take the one with the highest probability, and that's this one, and that is our thumbs down. So that's what the classifier would actually predict, that this is a negative sentiment, right? This string over here would return negative as sentiment. So this is in a nutshell how a knife Bayes works. Very simplified, but I think it gets the point across. Now, one important thing to realize is that because we do these probability calculations, we actually have access to what the model thinks are important features for a certain label. So in that sense, knife Bayes is actually very transparent. We can access these probabilities and see what components make so that a certain classification is made. This is literally due to the fact that some have a very low probability and some have a very high probability under a certain class that we're interested in. And I think in general it's a very cool way to look at data, where we just want to consider the probabilities and not necessarily this complex feature space that we've looked at before. Obviously that has some advantages, but it's a very cool alternative way to look at data. And also on another note, knife Bayes actually turns out to be a very complicated, or at least a very harsh baseline model for any text classification task. So if you want to, for example, train a support vector machine that we will be looking at a bit further down these slides, or neural networks for one of the next videos, these are very fancy models, and they are often pretty close to the performance of simple knife Bayes, where you can just look at some probabilities and don't need to consider these very complicated processes. You just calculate the probabilities. So for that, I think it's also a very, very cool algorithm. Okay, so before we fitted this knife Bayes classifier, now note that this is actually not the syntax for this multinomial knife Bayes that I used in the previous slides. This is actually for the Gaussian one. So the multinomial one has the coefficients that you can access. The Gaussian one has sigma, and you have access to sigma for each of the classes. So you can say the 0th class, in our case, will be negative. It can also be something different, but our 1 is positive. So these would be the probabilities of all the positive classes. So you'll expect, I hope, that the positive words that at least we associate with being positive also get a very high probability, right? This piece of code right here, you don't need to know what this does. Basically, I concatenate the sorted vocabulary with the probabilities right here. And then because this is an array and this is a dictionary, these are sorted and these aren't sorted. I zip them so that they get this nice list, and then I sort them based on the probability, and I want the highest first, so I reverse it. This is this part in a nutshell. It's not important, just that you sort of know what is going on here. But what we end up with is the tokens that we were provided during training, and then the probabilities that the model associates with them. Now notice that you might have noticed this earlier, but these probabilities don't sum up to 1 for all of them, right? It's not like we have a sum over all probabilities. There's 1, everything is independent of each other, so they can have very high probabilities. And what you would expect, this is not the top 1 to something. This is, I think this was like 100 or something. I just scrolled through and waited for actual positive words to show up, because as you can see there's a lot of stop words here. So those actually have very high probability just because they're probable words, right? It's not necessarily the case that that these are they are very probable under a certain label, but they're very probable anyway. So you will see the same thing with the negative weights actually. So this also, just to note, this is the positive words, right? So 1. Okay, so let's see, we have love here, we have story. So these are apparently words that positively influence our classifications, right? Really, so some intensifier here. Show, which is probably something also common for movie reviews, so it doesn't necessarily bear some informative value, but at least you can see well as well. Great, just great, all these kind of words that we associate as being positive, so those also have high probabilities amongst the stop words. So you'll have to maybe filter for stop words if you don't want them in. That could actually help your classification task a lot, but you would need some list of words that you think are stop words. This count vectorizer that we used to actually construct these does have a parameter where you can provide these, so if you would be interested you could filter them out, and then hopefully you would be left with only actual positive words rather than a bunch of stop words. But just for example's sake, I think this is good enough. So just to sort of emphasize that we have access to these nice probabilities when we fit a naive Bayes model. So now that we've covered naive Bayes, we can get into a bit more complicated territory, and also a bit more popular territory for more advanced classification for text. Now, prior to the neural network uprise, I think SVM, so support vector machines, were the standard text classification model, and I think they are still very good. They sometimes beat more complicated neural models. They're very, very capable classifiers, so I thought it was cool to just consider using one. Now notice that this is just a vanilla implementation, and it's a linear kernel. What the kernel means we'll get into in a sec, but this is just some linear separation, much like logistic regression. So you might actually want to compare support vector machines to logistic regression, where we're trying to fit a decision boundary. Now the constraints under which this is done that make it a bit better than logistic regression we'll get into as well in a sec, but here we use the linear implementation. Now we might also say we import SVC, and then SVC might have a kernel which we can specify, and we can specify the linear kernel as well. But this SVC model tends to be a bit slower than just the linear SVC because it has a different backend to do the calculations. But this is only important when you're using scikit-learn. So we fit this on our train, we do predictions on our test set again, and we do the classification report. And as you can see, if we compare it to the other results that we had before, we can see that we're only doing slightly better, right? So again, this is supposed to be a somewhat fancy model, but it's It's not really outperforming our naive Bayes baseline as we would want to apply it. Obviously we can use it as our actual model, but yeah, if we consider naive Bayes being our baseline, we're not beating this 86 recall or F1 score by any margin. However, also note that this is sort of a standard setup, right? We didn't do any tuning, we didn't do cross validation, so we might actually be able to improve our performances. So this is what I did here. I constructed a parameter grid to tune the C parameter that comes with the SVMs. Now C is not too straightforward to explain, but basically it increasing it decreases the amount of training errors you can make. So a large C will try to perfectly capture the training set, but it also introduces many errors, and then it's prone to overfitting. So it's always important to just gradually increase C, or be very careful with this parameter in general. Make sure that you have like a good evaluation. So here is our inner, so CV here is cross-validation. We try to tune this one classifier on 10 splits. Now, this exact scikit-learn implementation isn't your explained nested cross-validation where we split off a training set and a test set, and then for that training set we do certain splits, and then for these splits we also do splits, right? This is just doing double cross-validation, so it doesn't necessarily qualify as nested cross-validation. You would need a bit more fancy implementation for this, but this is one way to at least do a separate cross-validation for tuning and then for evaluating your model. So we supply the parameter grid, we do grid search, and then we do an additional cross-validation here with the best model from the grid search. So this automatically retrieves the best one. We can put that here, and we also put our training and our training set and our labels. We say tenfolds, and we get these scores right here. Now notice that this cross-validate function is only in the most recent scikit-learn version. I think it's version 19. So if you try this and it gives you some error, it's probably not implemented yet in your version. But there's different functions to do this that look like this. Anyway, so this, after doing this outer CV, which is not necessarily outer CV because it's not a formal nested cross-validation, but at least doing the second cross-validation, you can see the test scores for each of the folds, right? So this is also, actually, this is missing from this part, but the chances are pretty high that C was actually pretty big for this, so either 100 or 1000 for the best performing model, because as you can see the training scores are very low, and this C parameter, as I told you, tries to minimize the errors that we make on the training set, and it does it very well. As you can see, we're almost perfect on the training set, but as you can see on the test set right here, we're sort of approaching this naive Bayes baseline. Now, notice that an actual majority baseline will be 0.5 somewhat, because this was a pretty balanced data set. So actually we're doing very well, but compared to our simple naive Bayes model, it's not super optimal. Okay, so I wouldn't be talking about this task if we weren't going to do some actual applications. So now that we've trained our fancy SVM that by some margin outperforms our naive Bayes model, we want to test it on some new data. And what better data to provide than these complicated sentences that I gave in the beginning? So let's consider these. So let's give an example sentence that is supposed to be negative. So this movie is really, really bad. And if we then transform, this is using the count vectorizer, transform this string into counts, and then we predict on these, based on these vectors, we get a negative label. Remember that 0 was negative. So we're correctly classifying this one, so that's good. Now if we say I really love this movie, we get positive. So that's great. It's working, right? Well, let's consider the previous challenges that we posed, because you will immediately see why this is such a hard task, and you need so much more data and a more fancy model and actual good sense of what your data is, because if we plug in these 3 sentences, you can see that it totally mispredicts them. So this movie is only slightly better than Jaws. It's supposed to be a big compliment, yet the model predicts it as being negative. I love this movie as much as my headache. Probably negative, right? But the model predicts positive, probably because it has no idea from these movie reviews that a headache is actually negative, right? And then similarly, this negative example, best movie ever, not. Very, very sarcastic, yet the model still thinks best movie ever, so yeah, definitely a positive sentiment. So hopefully this proves my point that this is actually a very challenging task, and it can't just be solved with loading some data and fitting some models, even though they perform very well on the tasks that we set out and the data we collected. This is actual generalizability that we're testing here, right? Does it apply to some of the sentences that we think it should be classifying correctly? So we looked at support vector machines, but I didn't explain how they actually work. One of the reasons for this is that they're actually mathematically pretty complex and way out of scope for this course. But given that they're so effective, I just wanted to leave you with a at least high level intuition of how they work. So there's 2 important considerations, and one is that, very similar to logistic regression, we want to fit these kind of decision boundaries to split our classes in this feature space. However, doing this with logistic regression might give you something like this, right? So we have our one class here, just in a very optimal example, totally not realistic. And we have some other classes here. Let's make nice crosses. We might fit a decision boundary like this, right? And we're doing very well. So this is then logistic regression with a single decision boundary. And we're doing well because we split these correctly. Everything on this side will be one class. Everything on that side will be the other class. However, we might argue that the position of this decision boundary is actually not very good, right? Because if we would get additional samples that are actually pretty close to these dots over here, there's actually a pretty big chance that they will be somewhere around here, because these are, we can consider these ones the most problematic instances, right? Because they're closest to the other groups, so they are usually very similar, yet they are different. Now the chances that we will get these additional ones here and then some crosses there are actually pretty high. So what we would rather want to do is fit a decision boundary that has some maximum margin, as this is called, between our group here and our group here. So we want to have this space separated in a way that fits a decision boundary with a maximum distance from these groups, so that if we get any data that is closer to this group or this group, it will still be classified correctly. This is exactly what support vector machines try to do. They try to fit this decision boundary in a way that maximizes the distance to what is called the support vectors, and those are the most problematic cases, so the edge cases. And we'll look at an actual visualization that is not a doodle in the next slide, how this looks like. So these are the support vectors. That's one. And then another thing we want to do is we want to tackle nonlinear relations. Now, given that we only use this feature space and we have a decision boundary, it's not very trivial to do this nonlinear relationship classification. So consider, for example, a space like this. This is problematic, right? Because we can't draw one linear decision boundary that splits these dots at the side from the axis within. I can't draw it like this. I mean, I would need a lot to get them separated, but one single one won't work, right? And that's what we're interested in. So we apply something that's called a kernel trick, and I think that best serves itself to be visualized rather than being drawn, so I included a nice plot for this as well. But let's first look at the support vectors. Now, as I said, the support vectors are the edge cases. So hopefully you now understand why we want to fit this decision boundary here. Basically, what support vector machines do is they try to determine these lanes. So a sort of rectangular shape matching the coordinates as closely as possible between these groups over here and these groups over here. Now, using more support vectors here is going to shift this line somewhat, because if we want to be in between these support vectors for this decision boundary over here, actually we can name them differently. So if this would be our main decision boundary, say H1 for hypothesis 1, then we actually create two more. Now let's refer to this as H0. We create two more, so we have H1 and H2. So implicitly we fit two extra decision boundaries, one to be as tightly fitted as possible to the support vectors, so the most problematic instances on the side here, and then one that is most closely fitted to the amount of support vectors that we use from this group. So if we would use 3, this would be somewhat here. And then we try to determine our actual decision boundary in between H1 and H2, where everything on this side will be one class, everything on this side will be the other class, and everything within H0 will be 0, and then everything within the lanes over here will also be either this class or this class. So we have the support vector machines, we try to fit a straight line over there, straight decision boundary, the second decision boundary, and then the actual decision boundary, where on this side it's one class and on this side it's the other class. We fit literally in the middle. So this kernel trick that I promised I would give a visualization of, this is it basically. We want to transform our space using a kernel method. Now a kernel method applies a certain mathematical function to the coordinates of our instances in a way that changes the shape of the space. So we can go from this sort of ostensibly looking flat space. Now, even though this might be in 3D, the instances in reality might have somewhat bunched up. So let's say we look at a 3D plot, and then these red bubbles might actually be all around here. So like this. And then in the middle we have our crosses, right? This is still not linearly separable, even in 3D. But if we transform them in a way that we fit this sort of polynomial shape to it, we offset the sides to be higher in a certain dimension, and these ones to be lower, right? And once we apply this transformation with this kernel method or kernel trick, as you can see, now the problem is linearly separable. We can just fit this hyperplane decision boundary here, and we're done. Now we can use any other type of kernel. There's many types. This is almost a research field by itself to develop these special kernels for special problems. The most popular one is this polynomial one. There's also a radial basis function. There's a linear one that just does no transformation. or at least tries to adjust the space as little as possible. And there's many more. But this is what they do. So they transform the space in some way that it becomes linearly separable. One of the things they can also do is, for example, unroll this sort of Swiss roll deal, or a swirl, whatever you want to call it, where all the dots are here and then all the crosses are actually in the middle. So it can unroll this into a flat structure so that we have something like this. So very powerful classifier. It can become very complicated very quickly. It is therefore also prone to overfitting, but when evaluated correctly, it works very well. So especially for text data, one of the more important classifiers to consider. So we've arrived at the end of this video lecture. If you have any questions, please ask them on the forum, and I will see you in the next video.